Previously we have covered how we can calculate twist and shear stress on cylindrical or round cross sections. Well, on this video we're going to focus on how we can do the same thing on rectangular cross sections. For calculating the twist and calculating the shear stress, the basic equations remain pretty much the same. The change of the angle delta gamma will be still torque multiplied by the length of the profile divided by second moment of inertia multiplied by g. But now the difference is that in how we calculate the value for second moment of inertia. On rectangular cross section, the equation for calculating the second moment of inertia is as follows. Ix equals to alpha times h multiplied by b power to 3. So what is h and b in this case? When we're talking about rectangular cross sections, one of the sides is longer than the other. In this equation, it is always so that the longer side of the rectangular cross section will always be h. That rule is also stated on this rule in here. So if this h would be 20 and the b would be 10, in this equation we would have here 20 times b, which was 10, power to 3. Well, what about the alpha? Now we know how we calculate what are h and b, but what is the alpha? Well, alpha is defined using this table, which is also provided in the list of formulas. On this table, you can see in here we have relationship of h divided by b, and then we have these values in here. To choose the alpha, you first must calculate what is the ratio of height divided by the width of the profile. In this example, when we have, for example, 20 millimeters height and width is 10, it means that the ratio h divided by b will be 20 divided by 10, which will equal to 2. So in that case, when we are choosing the value for alpha, we would focus on these values in here, since the ratio that we calculated was 2. And now, using this table, you would choose alpha from here. The value for alpha would be 0.229. So that's how you would calculate the second moment of inertia. What about the section modulus? Well, on the equation for the section modulus, the equation is basically very much the same style as it is for the second moment of inertia, but in here we just have to use this value for b, beta, which we also get from the exactly same table, and using the same ratio of height divided by width of the profile. And in this example, if we have the cross section of 20 millimeters by 10 millimeters, we would have to choose the beta of 0.246. And then we multiply that by the height and the width power to 2. And from here we can see that the units are exactly the same as they were before. So this one will be millimeters power to 3, and this one will be millimeters power to 4, like so. So what about calculation of stress using the section modulus then? In rectangular cross section, the stress distribution is slightly different to what it is with cylindrical cross sections. In rectangular cross sections, the maximum value for shear stress is always in the middle of the longer side of the profile. In this example, the longer side is this one here, or also this one here, and you can see that the maximum value, tau A, it is on this location of the profile. To calculate the shear stress value, or the maximum value for shear stress, you use this equation, which is torque divided by the section modulus. Section modulus is calculated using this equation. Well, in some cases, you would also be interested in calculating the shear stress on the shorter side, this side here. This value is smaller than the tau A, and to calculate the shear stress on the shorter side, we use the equation where we get to use the eta. So tau Z is eta times tau A. And where do we get this value? Well, we get it from the same table as we took alpha and beta. So using these basic formulas, we are capable of calculating things like shear stress and also twist on rectangular cross-section shaped profiles.